Hi everyone, welcome to the people here in Wellington, as well as the people watching from the offices and other workplaces. We're very privileged to have a very knowledgeable person in Frank O'Callaghan here from Iplex in Palmerston North. I happened to talk to him in December, ask him a couple of questions, and I realized what a mine of information he is. So without further ado, Frank, please take the floor and tell us about your work with standards on the Joint Standards Committee, as well as at Iplex, and all of the wonderful things that you've brought along today. Thanks.
Thank you very much. Well, thank you for those kind remarks and for the opportunity to share some of our information with you today and with people who are participating at a distance. So I'm Frank O'Callaghan. I'm the National Technical Manager for Iplex Pipelines in New Zealand. We're a PVC and polyethylene pipe and duct manufacturers. But today I want to take my Iplex hat right off and just in a decommercialized way generally share information with you on electrical ducts and conduits made from PVC and polyethylene, and just have a look at some of the changes in standards, manufacturing standards that have happened in recent times, and also look at the materials that are used for these applications and some of the implications around how they're used. So going, or is it not going? Right, good. So these are the things that we'll cover today. Those of you that are here physically in the meeting have got a copy of our main catalogue for technical reference, which is also available on our website. So I'll give you a bit of information a bit later on where technical resources can be found. So these are some of the things that we'll have a look at today. Just a bit of background on materials and standards. We'll look at PVC and polyethylene because they are somewhat different in the way these materials are used in this type of service. We'll look at installations and fitting systems, the sustainable side of manufacturing conduits and ducts. We'll look at above ground applications, and we'll look at the findings of an important research project on the effects of weathering and UV exposure on ducts, which has got some really useful information. I think it will be helpful to the industry, and look at some of the technical resources that are available. So to begin with, we're looking at electrical ducts and conduits, and we're looking at really two materials that are used to manufacture these items, either PVC-U or unplasticized PVC, or in the modern era, a type of polyethylene called PE100 or high performance polyethylene. So it's important with PVC-U to know that there's a distinction between duct and conduit. And in the standards, both in the old standard and in the new standard, this distinction is there. And really, that one is not the other. That's the important thing, both in terms of their usual application, but also in terms of their dimensions. So ducts tend to be used primarily below ground and in fairly large diameters as well, whereas conduit tends to be used more above ground to shield and also identify electrical services in factories, in buildings, and these two examples here fairly typical examples of grey or orange conduit used in a factory situation. So let's have a look at the manufacturing standards. There's been a lot of questions raised in the marketplace about the changes in manufacturing standards that have occurred in recent times. So AS/NZS 2032.2, we're all familiar with that standard. That's the old standard. And that document covers PVC ducts and PVC conduits. And that's the document which will be withdrawn. At the present time, the old standard 2032 and the new standard 61386.21 are running in tandem with one another. They're running together, and that's referred to actually in the standards document. But within the next possibly year and a half, that's not something that we as a producer have got control over. 2032 will be withdrawn, and AS/NZS 61386.21 will replace it. 61386.21 is largely based on the IEC or ISO standard, the European standard. And so those two standards there, they are relevant to PVC ducts and PVC conduits. Ducts that are manufactured from polyethylene, on the other hand, are not really covered by those standards, and they were and still will continue to be primarily manufactured using the dimensions of the AS/NZS 4130 standard, which is the same standard that's used for manufacturing polyethylene water pipe. And the easiest way to think of this is that a water pipe with a blue jacket, which is then magically made with an orange jacket, becomes an electrical duct, just doing that. The material and dimensions and physical standards for a given SDR really don't change. And that's done like that because 4130 provides a platform for doing mechanical testing and also for closely controlling the dimensions and other test requirements of the pipe when it's made. So if we then think about PVC ducts, which are 80 millimeter diameter and smaller, and these are ducts, remember, that are used underground, the way that ducts are produced in New Zealand and Australia is by basing the standard on AS/NZS 1260, which is the manufacturing standard for PVC gravity sewer. So again, there's complete OD compatibility, at least in New Zealand, tooling wise and dimension wise, between PVC gravity sewer, or DWV as it's known, and the equivalent product, which is used for electrical duct applications. Electrical conduit in the smaller sizes is covered under the 61386 standard. An electrical conduit is manufactured from 50 millimeter and down and is a different product. Its formulation is quite different to give it an extremely high standard of malleability, so it can be physically bent. It has extremely good resistance to low temperature, and it is manufactured to metric OD dimensions, and even the fitting systems that are used with electrical conduit, as I'm sure you know, are a different range of fittings to those that are used with duct. And if we keep those sorts of distinctions in mind, then it helps us to understand other things that we will see as the products become used in the marketplace. So just, yeah, okay, I flicked forward one. So if we think now about the duty classifications that exist for PVC ducts in particular, there's been a lot of questions about that. So AS/NZS 2032.2 has 4 duty classes in it that are called up: VLD, or very light duty, right through to HD, or heavy duty classification. And with the adoption of the new standard 61386, there have been 5 duty classes appear, so very light duty through to heavy duty. But there's also an additional class that's appeared in 61386, which is called VHD, or very heavy duty. The easiest way of thinking about this is that if we think about the origin of 2032, 2032 was developed at a time before there were any other standards for plastic electrical duct. And so the dimensions of, we just take heavy duty, for example, of pipe made to 2032.2, were actually based on the wall thicknesses of pressure pipe. And that really created a duct which was hugely thick in the wall, expensive, but also with a tremendous amount of weight and performance, which is totally redundant for an electrical application. It's not a pressure pipe, it's an electrical duct. And whilst its SN class is very high, this product is sort of an SN 40, the performance capability the product has was and is largely redundant. And so that was recognised when the new standard 61386 was adopted. And so the equivalent under the new standard is a product called heavy duty, which is, you see, this is heavy duty. This is heavy duty under the new standard, but this is an SN10 product. And it actually has the same stiffness and the same wall thickness as what it would be if it were a gravity sewer pipe, also performing a heavy duty performance capability. So the easiest way to think about this is that the adoption of new dimensions and stiffness classes in the new standard has really rationalized the range and created a range of product which is much more suited to the purpose that it's actually being asked to perform. The smaller sizes of PVC duct, that's DN32 through to DN80, were and still are manufactured to a nominated wall thickness in the standard. They don't have an SDR, they don't have an SN class, their wall thickness is nominated. And an example of that would be something like that. So what that actually delivers though is a product which has got a duty classification which is somewhat above heavy duty in all the sizes, just by default. And then if we think about polyethylene, which is based on the 4130 standard, polyethylene pipes like these are nominated for electrical applications by their SDR, by their standard dimension ratio. SDR 17 and SDR 11 are the most common ones. So if you look at this DN32 duct here, that's what SDR 17 looks like. And of course that becomes important for horizontal directional drilling applications, where you have to have a pipe that's thick enough so that it actually can be drawn into the ground off a large coil and have sufficient strength to remain round and structurally sound for purpose in the ground. So there's a range of SDR 17 and there's also a range of SDR 11, and there's always a debate that goes on amongst the asset owners of which one they're prepared to pay for. SDR 17 is a lower cost pipe, but it's got a lower level of tensile performance. SDR 11 is a somewhat higher cost pipe, but it's got a much higher standard of tensile performance for drilling. Yeah. Okay, so if we think about what the equivalents in stiffness are, we just simply look at the old standard 2032.2 and you can see the classes there from very light duty through to MD, and I put in what the approximate SN stiffnesses are. You can see VLD really doesn't have one, it's probably more like about SN4 or thereabouts. But under the new standard, you can see where the SN classes fit. And so if we look at it like that, we can see straight away that there's some functional equivalent there between the old standard and the new. And the easiest way of thinking about it is that what was heavy duty under the old standard and what is heavy duty under the new standard have the same functional performance capability. So you don't forget about SN class, just think about what the pipe is delivering. And that is the easiest way of thinking about it. Under the new standard, you've got this fifth class, which is called very heavy duty or VHD. And we get asked, where would you use that? And the answer to that is that you would get the performance out of it where the duct is extremely shallow. So for 600 millimeters deep or more under a sealed carriageway, your HD class, your heavy duty class is going to do it all. It really is. But very heavy duty would come into its own where the duct is shallower than that. And there are situations under roads where you just don't have the cover. So if you've got 300 of cover or maybe 400, 450 of cover, then the VHD duct actually does provide some additional performance for the additional cost. As soon as you get out of the carriageway and under berms and into areas where there's no traffic loading, then the other classes come into play. And the LD or light duty duct would probably be the one that you'd use as the standard duct. VLD will certainly do the job. If you're on private property, it will definitely do the job. But for those asset owners that want a slightly increased level of factor of safety, then LD will do the job very well, providing you're out of the carriageway. Is probably the best guidance I can offer. Okay, so as soon as you put concrete slab over the top, yes, okay, I'll get to cast in a minute. So if you put a concrete slab over the top, it's the concrete slab that's carrying all the load. So straight away, you're into either light duty or even very light duty territory, just doing that. If the pipe is cast in the concrete, either light duty or very light duty duct would also be good options. Encasing the pipe, because it's not a pressure pipe, encasing the pipe in concrete doesn't do the pipe any harm, particularly. Yes, okay. So it's a decision you'd have to make based on how much concrete you've got going in there. And it would have to be an extremely large amount of concrete put in at a very high flow rate to collapse even very light duty pipe. I would say this here is what light duty looks like. And that product, if it were a gravity sewer pipe, I would say that's concrete encased routinely all the time. Pressure pipes are different for reasons I won't go into now. But that's really the situation. Putting concrete around it doesn't affect duct really at all. Not even the heat of hydration commonly is an issue.
We had a situation in Auckland when a vertical column was cast,
yes,
and it was quite tall.
Yes.
When they installed probably very light duty,
yes,
and it collapsed under the pressure.
Yes.
So I think, you know, when the pressure is rising, the concrete is quite heavy.
Yes.
That's definitely something that you should specify.
Yes.
That they need to go to a higher.
Yeah, and so HD would be a good general purpose option. The VHD, the extra structural performance that you get out of VHD, which is SN25 versus SN10, really doesn't offer too much extra benefit unless the pipe is under very direct structural load, which you'd normally expect from traffic where the depth of cover is very shallow. The SN stiffnesses for the pipe, as I indicated on the previous slide, are known. And it's not too difficult if you need to do the calculation to relate the depth of concrete and the amount of load that you're putting on the pipe using Timoshenko's relationship or something like that, and then just pick the pipe that's appropriate. Yeah. Okay, so we look at PVC electrical duct systems in the modern era. Most electrical duct manufactured certainly to the new standard, you will encounter it looking like this, where the pipe is orange on the outside and will have a white core. And that's exactly the same technology as used in manufacturing the same size pipe for gravity sewer. In the manufacturing process, PVC and polyethylene are very recyclable. And so the material that is the wrong shape or the wrong size or whatever is ground into small chips and put straight back into the process. But because it's not perfectly orange, the technology allows it to be put in the middle of the pipe where you can't see it. It is the same material, it's just a different color. And you will encounter most of the ducts that you will encounter See that there's a piece of, that's a piece of SN10, that's a piece of heavy duty made to the new standard, and you'll see where it's chamfered on the end, and it's got that white core, and that's all it is, it's just a change of colour. And that's to make the production process efficient and sustainable. So electrical duct fittings are typically of the style shown in the image there. So they are formed from the duct, usually manufactured from heavy duty duct to allow for the bending process. And the majority of duct that's made is joined using PVC solvent cement and cleaner primer. Exactly the same process that's used for joining gravity pipes in other systems. We, as a manufacturer, recommend that cleaner primer be used together with solvent cement always, because with these systems, you want the joints to have a high standard of integrity, and so you have to do that by using cleaner primer. In seismically active conditions, a good option is to consider using rubbering joint instead of solvent cement joint. You don't have to use solvent cement, or don't have to use rubber ring on every pipe, but it is certainly possible to introduce rubbering couplings like these into systems if you want an additional amount of seismic resilience, which is really only important in ground which is liquefiable. As soon as you get out of ground that's into solid ground, liquefaction really doesn't occur, and solvent cement joint would generally be satisfactory based on our experience with gravity sewer. So now we come to electrical conduit and fittings. So electrical conduit, as I said before, is a different range of dimensions. So it's metric OD dimension product, and it uses a special range of fittings, which are very typical of the ones that you see there, to allow access into the system and to provide shielding for electrical services above ground. So I've just given you a couple of examples there. One is the use of the orange product above ground, but where it's shielded from direct sunlight so that the orange colour remains over time. Or if the product is exposed outside, and here it is sitting on the side of a large factory wall, then the grey version of the product comes into play. Same product, same dimensions, but the grey formulation is set up to provide a very high standard of resistance to change of colour due to UV. So this grey product here put outside will give you possibly in excess of 30 years, maybe even longer than that. We've got experience up to 33 years with white pressure pipe using this formulation, but it's an extremely long period of time. Whereas the orange product will fade. It'll go from orange to white if it's directly exposed to UV. But I'll talk a bit more about that in a minute, because that doesn't necessarily mean that the product is unfit for its purpose mechanically. So PVC ducts and conduits are all manufactured in the current era using sustainable production technology, and they're manufactured using a process called CX, or co-extrusion. And so this pipe here is manufactured using 3 material streams, one to give you the coloured bore, one to give you the coloured exterior, and one to give you the rest of it, like that. And the device there on the right is just what a recycling grinder looks like. So if the pipe is to be recycled, it's just put through that device, and it instantaneously turns it into fine chips, which can then be put back into the process. From your point of view, it doesn't alter in any way what the duct is, what it is mechanically, or the service that it performs. The only time you'll ever see it is the slight change of colour on the end. Other than that, it's something that you can ignore from an asset point of view. So we've talked a bit about PVC. Now let's talk about polyethylene. So polyethylene in the modern era is in the smaller sizes, these sorts of sizes here, is always coiled for electrical applications. It's a PE100 material, and DN32 pipe like this here, which is SDR17, would typically be in 1,000 meter rolls in the current air, or a kilometer on a coil, and you can see some of those on the top left on the screen there. And the technology to coil polyethylene is growing all the time. So probably as recently as 2.5 years ago, we were probably only coiling up to about 110 diameter, about this kind of size. But we're now routinely coiling DN140 for electrical applications, and DN160 is now being coiled. Some of that's being used in Auckland right now. And within the next year, certainly, you'll start seeing coiled DN180, which is even bigger, appearing in the New Zealand market. But if you look at internationally what's going on, polyethylene pipe is coiled internationally up to 0.5 meter in diameter, that kind of size. And the limitation on what you can coil is really just controlled by the capability of the equipment you're using. In New Zealand, or particularly for this size, DN160, we're at the point now where we're transitioning from straight links, which you can see on the lower right side of the screen. So those are 15, excuse me, 15 meter lengths of polyethylene pipe. And that is really where the development is happening. The coil on the right is DN140, so that's that kind of size. And I think that coil's got about 300 odd meters of duct on it. So from the asset owner's point of view, that can be quite attractive because it greatly reduces the number of joints that are actually in the duct. And from an installation point of view, it reduces the amount of time involved to do either mechanical or electrofusion joints. But on the other hand, it places some obligations on the drilling contractor, the installer, on the equipment he has to have to achieve a successful outcome, particularly with those big coils. So there's just a close-up there of what lengths and drum coils look like. The drum coils, that drum coil there, the dimensions of it would be a little bit higher than the top of that ceiling there. So that's an indication of how large they are. And pipe supplied like that requires a contractor with the right skill set and the right equipment to be able to turn that coiled pipe into a successful asset in the ground. Just as a quick reminder what horizontal directional drilling looks like, the process that's used with electrical ducts is the same as is used for water pipe, where a drill puts a pilot hole through. So you might just put a pilot hole through under the ground here by this building and have it come out on the other side of Te Papa, typical example like that. Pilot holes put through, then it's back reamed and enlarged sufficient number of times. And then on final pass, the duct is hooked on to a pulling head and pulled through the hole together with a certain amount of drilling lubricant in the hole to smooth the path of the pipe. It is a reality of working with larger diameter polyethylene ducts, and it's really important with DN140 and 160, but possibly with 110 as well, that the pipe needs to be re-rounded and straightened before it enters the drill hole. So polyethylene, PE100, is a viscoelastic material, and its memory, it has quite a strong memory, is of being straight and of being round. That's what it was when it was extruded and in the molten form. But the process of putting it on the coil forces the pipe to be slightly oval, and it also puts a certain amount of curvature in it, as you can see by these short sections on the left that have been cut off a coil. And that curvature and the ovality in the pipe, if the pipe is just taken off the drum coil and just laid out along a flat surface somewhere and left relax in the sun for a day or two, most of that roundness and ovality and out of straightness will revert. Not all of it, but most of it. But the reality of working with coils is that the pipe has to come off the drum coil and go straight in the ground. And so the technology exists to allow that to happen with this large diameter product, and that's a rerounding device. This is a McElroy line tamer here, which is just one example of technology. And all it is just two rollers which grab the pipe as it comes off the coil and just force it back in the round again, just in one step, bang, like that. And also take the coiled pipe that's coming off the drum coil and force it to be straight. And it causes the reversion to happen quite quickly so that the pipe that comes off and then goes into the hole is straight and round, or nearly round. And that's a reality. That's the other side of working with coil pipe in these big sizes. One can't escape from the other. It's not a problem, it's just a requirement of the process. So the other thing we need to do is make sure that the pipe is not damaged in the drilling process. And I brought this piece of pipe in here to illustrate what can happen if things go wrong in the drill hole. So this is not the fault of the pipe, it's the fault of not knowing enough about what tensile loads are being applied to the pipe in the drill hole. Probably in this case related also to the drill hole not being big enough and probably not very well lubricated. But the main problem is that the contractor did not know how much tensile load he was putting on the pipe. And he's put too much on, and that has induced the pipe to go from its elastic deformation form, if you will, through to a point beyond yield where it assumes a shape which it then doesn't return from. That type of thing can be completely prevented if the drill has got adequate control of the tensile load being applied to the pipe. And so that is why in that catalogue, and I've noted it up in there on screen, alongside each pipe, we've actually nominated the maximum allowable tensile load which you can apply to polyethylene duct in any one of the sizes. So that's just a maximum number in kilonewtons, and that's based on the hydrostatic design stress of the material to make sure that we are a long way below the point at which we go beyond the point of elastic deformation and go into a point of permanent deformation in the material. What we're encountering are some contractors who are used to working with small diameter pipe in the water market, and they're finding opportunities in the electrical market, and they're getting into installing electrical cable duct, and particularly in bigger sizes. And probably the technologies that they're using with smaller diameter needs to be substantially upgraded to get the right result with these larger pipes. But if the technology is there and it's done properly, then it can create a very, very nice asset for the asset owner. So polyethylene duct cannot be joined by solvent cement. So the jointing systems for it are either electrofusion, which is a common system used with water pipe, or it can be in some sizes mechanical. So mechanical fittings like these, which are currently available in the New Zealand market up to at least DN110, are a really good option for coiled polyethylene cable duct because they have a rerounding effect on the pipe where the joint is made, but they also act on the outside of the pipe and they don't interfere with the bore at all. So the internal diameter of the duct is maintained all the way through. And so duct fittings like these smaller ones here, whether they be used on SDR 17 or SDR 11, it really doesn't matter. A really good option, very fast to install, and again have a rerounding effect. They are available either as a screw-up style of fitting, which can be reversed if necessary, or in some of the smaller sizes, they take this form here, which is just insert and lock. Insert and lock. So you've got 1,000 meters here, 1,000 meters here, put one of these between them, and you've got a section of duct that's 2 kilometers long, just in one step. In the bigger sizes, electrofusion is probably the main option. Anyway, a joint system which doesn't interfere with the bore of the pipe. We don't use butt fusion because it forms a bead on the inside of the pipe which interferes with the pipe's bore. So all pipe that's coiled, and it doesn't matter what size it is, but all coiled pipe assumes a certain amount of ovality in the coil, and the ovality, particularly in these bigger sizes, does not reverse by itself within a manageable time frame. And so if you lay that pipe out in a paddock and leave it in the sun for a week, it'll be pretty round by the end of the week. But we want it to be round within a much shorter time frame than that. We want the pipe to come off the drum coil and go straight in the ground. And so where we're joining product, particularly with electrofusion, it's necessary to use a couple of rerounding clamps to force the pipe to be round at the point where the electrofusion joint is being made. Now that is the case with all polyethylene pipe. Water pipe, sewer pipe, electrical duct, it doesn't matter. The pipe needs to be helped to be round right at the joint. Polyethylene, of course, is also a very recyclable material, and you will see in the current market that the vast majority of polyethylene pipe, whether it be small or whether it be large, uses CX or co-extrusion technology to colour the outside of the pipe. So there'll be coloured jacket there, and the rest of the pipe will be black. So that means that material which is available for recycling in the production process can actually be recycled. Now, the production process is the same for all types of pipes, so it doesn't matter whether it's comms duct, various types of comms duct here, or whether it's water pipe, or whether it's gas pipe. The inside of the pipe is the same, and it's only the bit on the outside which is coloured according to what the performance function is required to be. So you can see there the type of granulator. It's very similar to that used with PVC and what granulated polyethylene looks like. So that's material which has been finely chipped and can be reprocessed. So we get asked very often about recycling material off work sites. And the reality is that although this material is very recyclable, the other stuff that comes off a work site, which is bits of wood, dirt, little stones, bits of metal, and everything else which is not polyethylene, is not recyclable, obviously. And this here is an example of what happens or what can happen with material that's been taken off a work site, which is polyethylene that's been contaminated with nylon, which is the material used in the strapping on the coils, which is incompatible with polyethylene. You can recycle nylon as well, but you can't recycle them together. And so the best advice that I can offer for an interest in recycling or post-consumer material off work sites is the first thing to do is to actually recycle it at source. Take all the short bits and join them together and use them all up is the best advice I can offer. On the lower right side there are packs of PVC cable duct off a large roading job north of Auckland, which were never used and then offered in very heavily contaminated condition for recycling. So unfortunately, there was no interest there in trying to use that product up or consume it. And because it was allowed to become very grubby, it became impractical to recycle it at the factory level. But on the lower left side is a sort of recyclate that we very commonly see, and it's an absolute dog's breakfast. It really is. But I would strongly advise all owners of assets and all people working with materials like these to think about recycling, and the best kind of recycling that you can do is to use it all up on site. Join it all together and use it. So above ground applications, we know from doing UV testing, which I'll get to a little more in a minute, that ultraviolet light is not reflected off surfaces. And so surfaces like these, whether they're either grey or orange, put in the shade, permanently shaded like this, can be a very, very good long-term solution. So this is a shot over River Bridge, not very far from Queenstown Airport. And you can see services, electrical services that have been run across the underside of that bridge, and they will remain there permanently. They're not affected by frost. They're not affected by corrosion, providing the strapping is suitable, and they are allowed to expand and contract between summer and winter, between day and night, and they're really very good lightweight option to enclose those services running across the bridge. But if we're looking at exposed applications above ground, then UV ultraviolet light comes into play. And so one way of dealing with that is to, particularly with conduit, is to utilize the technology which is in the conduit, which is grey, not orange, and which is inherently very, very UV resistant. And we're protecting it not so much from brittleness, we're just protecting it from color change. So if we put it up as grey and it stays grey. There are some applications, in fact quite a lot of applications, where orange is used successfully above ground, where the application is shielded from direct sunlight. But there's no escaping that orange exposed to the sun doesn't stay orange. So these two samples that I've got here were actually exposed in a UV test, which finished only this month, earlier this month. And these two samples have, well, that one there has been exposed for almost exactly 24 months, 2 years. And so it started off as that, and it's now become that. And really the only effect that the sun has had is very cosmetic on the surfaces to make it paler, to whiten the material. But the mechanical strength of the material is not totally identical, but it's largely unchanged. It's certainly completely fit for purpose as an electrical duct. And so that faded material, rotated 180 degrees, suddenly becomes orange again. And can be used, because if that were buried in the ground, it's only the top that you see. And there's a lot of orange duct which is faded or has undergone color change, where it's been stored on work sites and so on, which is just rejected or thrown away and still has a useful purpose. And so the UV testing that we've performed indicates, it certainly indicates quite clearly that the UV is not reflected. It only affects the part of the duct which is directly exposed, and that it has to be exposed to the sun for a very long period of time for there to be any significant brittleness start to appear in the product. So it's one thing to think about, that just because an orange duct is a little bit faded like that, providing it's not been exposed for many years, and it's only been exposed just in its storage crates or whatever, is not grounds for rejecting it. It can still be used because there's still an orange side to it. We just use the orange side that's already there. Okay, so the reality of a lot of work sites is that there's, you get very, very crowded easements. And so I put these slides up here really just to show that having a good, tidy approach to the way that all these services are put into a work site is pretty important. So this is not far from Mackay's Crossing on the Peka Expressway when it was being built. And you can see in that hole, we've got stormwater, we've got sewer, we've got electricity, we've got communications, and we've got water main. And they're all in the same hole. And they've got them organised in there so they're a specified distance apart before they're bedded and then properly identified above the ground. The question comes up sometimes where you use cable slab or mag slab or something like that above buried electrical services. And really what it comes down to is whether you want or whether you think you want an additional amount of identification of where the duct is or not. I kid you not, if you've got a 20-ton excavator digging a hole, whether mag slab is there or not, or whether it's heavy duty or very heavy duty or not, really doesn't matter. The teeth are just going to go straight through it. So the important thing is to understand where the assets are, and just coloured tape like that above the duct certainly can give you some identification. But our experience is that putting in a mag slab above the pipe actually doesn't add really anything in real life to its ability to resist mechanical damage. But it may add something in terms of helping to identify what's there. Yeah. Okay, so those are the main things that I wanted to cover with you. In terms of where there are technical resources, there's extensive technical resources available in the marketplace from various sources and suppliers. This is where our resources are. Find them on the website. Okay, and there are also contractor installation guides which are available from us and other participants in the marketplace. A lot of these guides are based around installation of water and sewer systems, but the basic requirements for doing solvent cement jointing of duct, or to do rubbering jointing of duct, or to do electrofusion are the same, regardless of whether the pipe is used for electrical purposes or used for water or sewer applications. And those are my contact details as well. I'm available almost 24/7 in the current era. So I'm more than happy to take inquiries, questions of any kind out of the marketplace, because from our point of view as a manufacturer, we have a very strong interest in a successful outcome with the products that we manufacture. We spend a lot of time and a lot of effort making sure that the dimensions and materials and performance in these products are to standard and will do the job they're intended, but we want those assets to be successful the first time. And I think that's what all of us who are involved in this industry would want. So there we are.
I've got a question.
Questions?
If you have a cable, if you have a cable and running into one of these ducts and it runs, say, at 55 to 60 degrees Celsius, how does it actually affect the strength underground? Will it weaken it? Will it create a problem? What's your experience?
At that kind of temperature, sort of in the 60 to 70 range, no. The extrusion temperature, or the temperature at which polyethylene melts, is typically about 195 through to about 210 degrees centigrade. And for PVC, about 180 to 190 degrees centigrade. So that's the melting point of the material. But these materials go through a softening phase below that. But the softening phase in these sorts of applications, gravity applications, really doesn't happen until the duct gets up to probably the low 90s, you know, in that below 100 degrees. I mean, so you can put this material or that in boiling water at 100 degrees centigrade, and it would still have a very high standard of mechanical strength. Although, if it were a pressure pipe, it would burst almost instantaneously. But at this temperature of sort of around 60, 65 or so, no, has no effect on it structurally that's significant. Even gravity sewer like this is capable of handling intermittent applications and discharges up to 70 degrees centigrade. That's a standard requirement. So these materials, basic materials, are the same. One thing that is worth remembering, though, is that the flammability of these plastics is not the same. One of the reasons that PVC is so widely used worldwide for electrical applications is because although it will burn, it doesn't support combustion. You take the source of ignition away and a material ceases to burn. Whereas polyethylene, on the other hand, is a wax-like material which burns literally like candle wax. And so if the material ignites, which is obviously not going to happen at 60 degrees, polyethylene will actively support the combustion activity, or support the fire, whereas PVC will not support it. It will just burn passively. And so in applications where ignition is an issue or a risk, then, and this may be above ground, maybe in tunnels or service ducts or that kind of thing, PVC would offer an increased level of factor of safety as a result of that, but only where ignition is likely to happen.
And with PVC, do you have problems if it burns with phosphenes and other nasty chemicals that come off? No.
I mean, say both materials produce carbon monoxide, which is just a product of the combustion, but there's nothing inherently toxic in the materials because the standards totally ban it. So there's no lead, there's no cadmium, there's no mercury, there's no heavy metals at all used in the materials. About the most damaging material that would come off burning PVC would possibly be chlorine-based residues, which are not, I mean, say they're dangerous if you breathe them in, but they're not inherently dangerous really to anything else. Polyethylene literally turns ultimately into carbon dioxide, carbon monoxide, and water when it burns. That's it. There's nothing else in the material other than polyethylene and carbon black that would be an issue.
And can you perhaps make a bend on site with polyethylene by doing some forming like you do when you straighten that?
With the smaller sizes, you just bend it. A piece of that pipe there, that's going to be a little bit difficult to bend because it's not very long, but a piece of this, the length of this table, can be hand bent quite comfortably into quite a reasonable radius. So the limit on how much you can bend it will be controlled by how much you can bend what goes inside it, rather than the pipe itself. Polyethylene can be bent to a much tighter radius of curvature, I would suggest, than what the minimum radius is that's allowable for the cables that are going inside it, that which limit the process. And also horizontal directional drilling the radius on that is limited by the flexibility of the drill rods themselves. So with polyethylene, it's not at all common practice to make up bends on site. You utilize the flexibility that's already in the material. With PVC, on the other hand, it is very common practice because it's a fairly rigid material. It's common practice to use dedicated fittings with it. And those fittings are available from us and others to a nominated radius of curvature. So you don't bend PVC on site, you use a fitting to create the bend. Because PVC in many sizes are incompatible with gravity sewer, that means that there's a potential to use some of the gravity sewer fittings to do quick repairs like that. or to provide access into an asset which is being put into the ground and then possibly put into hibernation for a while. So these can either be put on permanently or not. They have screw-on caps, they have rubber seals. They're not orange and they won't be orange, but they physically do the same job. Mechanically, they do the same job. With polyethylene, it's possible to do exactly the same thing. So in these sorts of sizes, you can cap the pipe off, you can join it to other pipe, but junctions and branch connections and so forth are always fabricated fittings to get the radius of curvature correct.
Now, if you look at the pricing of the polyethylene fittings, they're probably quite much more expensive than the PVC ones because they're so complicated and use so much material. No,
not really. I mean, say that a joint is what it is. So the alternative with polyethylene to a fitting like that is to use an electrofusion coupling, for which you require a fitting, an electrofusion control box, a source of electricity, and all of the preparation and rerounding clamps that goes with it. Whereas with this, you just trot onto site with a couple of wrenches and just join it. And whilst the fitting itself has got a cost associated, it's not an unreasonable cost, the speed and convenience of installation, particularly in wet, unfriendly conditions, you know, up on the wind farm where you're connecting ducts like these in the rain or in the mist, this sort of thing is a really good option. And the cost of the fitting is really not important. With PVC, solvent cement or rubber ring, that jointing process is what it is really.
We've just got one question online.
Yes.
Are there specific ducts used for electrical installations intended for renewable energy, such as PV system?
Sorry, please repeat the question.
Are there specific ducts used for the electrical installations intended for renewable energy, such as PV systems?
Oh, so such as solar farms?
Yeah.
Yeah, okay, right. So as I'm sure you know, electricity is the same regardless of the way it's generated. It doesn't matter whether it comes from solar or wind or geothermal or coal, heaven forbid, or any other source. Electricity is what it is. And so the answer is no. The same product would be used to give the same level of performance regardless of how the electricity is generated. It's worth also remembering that another reason that PVC and polyethylene are widely used internationally is because of all the materials, the synthetic materials that mankind has invented. These two are among the best electrical insulators of all. They have extremely good insulating properties, and you know, even in very thin sections, they just don't transmit electricity. And so, but from a functional point of view, structural point of view, the product would be the same. We do get asked sometimes, you know, would you use something different where you want an electrical service that's particularly sustainable? In the modern era where sustainability and recyclability is very important. And the answer again is that you use a standard product. These materials have very low carbon mile imprints because they're not imported from the European Union. The material is imported from other places, but the pipe itself is made right here in New Zealand. And so their environmental footprint with recycling in the factory and with the low cost of transporting the product, particularly in some of these bigger coils, is already very, very low. That's just an inherent part of the way the product really is.
Great, we've just got another one that's just
Yes.
come through. I'll check, does anyone have a question in here? And we might...
Just in terms of recovery and recycling of the PVC, what sort of percentage do you have coming through that are from existing buildings, which are clean and not contaminated ducts?
Very little. the reality in our business, I think we're representative probably of the manufacturing industry across New Zealand. I can only speak for us. But reality is that we cannot get our hands on anything like the amount of recyclate that we could potentially use. There are a lot of other polyethylene products that we make which consume recyclate. And there are some products, not electrical products, but some products where we use many tons a month, if we can get it, of recycled milk bottles, which is high density polyethylene, and that material makes beautiful subsoil drainage pipe. And it is physically exactly the same as if the material were made from virgin material. But it is the nature of these materials that once they go in the ground, they're in the ground. You don't really ever see them again. Materials that come out of buildings can be recycled, but as with all recycled materials, they've got to be separated from the contaminant load to actually make it economic. And in the current era, we haven't really quite got to that point yet, but there are various ways of recycling plastics. There's experimentation going on, I understand, in New Zealand right now, looking at using contaminated granulated plastics as a component in road seal. This material here, chipped up, makes a very good addition to certain types of concrete. Certain types of concrete. But the volumes are tiny. They're really tiny because the material just isn't available. It's in service somewhere and it's encapsulated and you just never see it again. But there is potential in the industry to get a lot smarter about the way that materials are being recycled and consumed on large construction sites. So it's basically being smart and moving from wasteful work processes through to more efficient work processes. And the joining systems are already there. It's just simply a matter of applying them.
Just one more online. Sorry, Daniel.
Yes.
To interrupt. And then just being conscious of time, I think we'll probably wrap up there. There's a question asking, are the materials corrosive resistant and can they be used in a chemical related environment?
Yes, very good question. So one of the very long standing applications for PVC-U, it's the same material as we've got here, is in the manufacture of sulfuric acid. Fertilizers based on sulfuric acid, also the manufacture of batteries and so on. PVC and polyethylene are two of the most chemically resistant plastics there are. So we see both those materials used very extensively in the chemical industry, where we're working with either very, very alkaline materials, sodium hydroxide manufacturing, that kind of thing. So the answer is yes, they're exceedingly chemically resistant. Both materials are. In an electrical application, there would be a very, very limited range of things that would have any kind of chemical impact on buried electrical ducts made from either material.
Frank, thank you very, very much for this talk. It's valuable to have your contact details so that when we have specific questions, we can contact you directly. Thanks for sharing that and for being willing to share your knowledge with us. Thanks for traveling here today, and to everyone attended here in Wellington and online. Thanks very much. And last but not least, Holly, thank you very much for helping us to organize this and bring this to the floor today.
Thank you. Well, thank you for the opportunity to share this information. I trust it's been of interest. I really had to choose what topics I thought would be of help. Very willing to take any other questions about anything at all that might arise in the future. So thank you. Okay, great.